Hi, GEO 102 Hybrid Summer 2019. I'm just going to help you fill in a few of the notes that we didn't get to in class, and I appreciate everyone's patience with making this video. So we're going to go down into the stuff that we didn't have time for really in class. We talked about clouds. Let's now talk a little bit about fronts. Now, I've already graded your workbooks at this point, so I can see that most people understand how warm fronts and cold fronts works, the basics. What most people drew was a block diagram, which is a more, it's absolutely correct, but it's more complicated than what you actually need. So this first question here is about warm fronts. So a warm front and a cold front both involve air masses moving over the land. In the case of a warm front, it's the warm air that's moving, whereas in a cold front, it's a cold air that's moving. And warm fronts and cold fronts are important because they can tell us a great deal about, or at least clouds associated with them can tell us a great deal about the weather that's going to be happening in the next few hours or days. So right here, I've started my drawing of a warm front. It's pretty lousy because it's in Paint 3D, but bear with me. And I'm just labeling this part here as ground. So you can see that we are kind of, this is the ground, this is this part right here is the flat part of the ground. We're looking from the side here. So what we're drawing is a cross section. So, warm front's pretty simple. Ooh, I lost my cursor. Warm front's pretty simple. Oh, where'd my cursor go? There we go. We're going to start down here. And this is the dividing line between the warm air mass and the cold air mass. So what happens in a warm front is this warm air is moving forward. So the warm air mass moves in this direction and slides up over the cold air mass. Now this little point down here on the ground, it's very hard to see my cursor in this. This little point right down here on the ground, just circle it, let me give it a different color. And circle it in red. This is where the front actually is. So when you look down on a map, that little point is actually a line that's moving. So when you drew those, you added to the diagram that that had the mid-latitude cyclone on it, those like scalloped lines and those pointy lines are represented by this single point down here, because now we're not looking from the top view, now we're looking from the side view. And so that warm air will come through. Now, one of the important parts of warm fronts and cold fronts and where they meet is, and let me actually label this down here as the front, make it a little clearer. As it moves, where that warm front and that cold front contact each other, that's where you're going to get your cloud formation. So these are my even worse than drawn in class. This is where my clouds are going to be, right here where the two of them contact one another. So I'm just going to go ahead and select and put this right into our notes. So right here. Now you can fill in these notes by hand. Let's now do the cold front diagram. So the cold front diagram is very similar to the warm front diagram, but it's shaped a little differently. The warm front has that low angle because what you have, oops, that's not, I wanted black, has that low angle because that warm air is sliding up over the cold air mass. In a cold air front, it's going to look a little bit more like this. So that cold air is basically plowing into the warm air front. So this is our cold air. And this is our warm air mass. And down here, once again, this right here is basically our front. This is the part that's moving forward. And this cold air front, cold air mass, oops, lost the cursor again, is running in this direction that you can see from this arrow right here. So we're just going to go ahead and we're going to add this diagram into this. And I know that the book has, it's a little more complicated. The warm air mass is being pushed, so they have an arrow that way, and they have warm air flowing up over this big mass right here. But these are the important parts. The cold air mass is moving forward. That's why after a cold front, we get, it feels cold. And just one last thing to add, I realized I forgot. This is where we're going to have these clouds. And here we have vertically developed clouds in association with the cold air mass. So you're going to see a lot of like cumulonimbus clouds. So it's something that we see in the summer a lot, right? These big, tall, dramatic thunderstorms. And those are very often caused by cold fronts moving through. Now we went outside, we saw the clouds today. If we saw a warm front cloud, this is like if we saw a warm front. Or if a warm front was coming, we would see wide, flat clouds because the front is wide and flat. So for example, nimbostratus, cirrus, altostratus, etc. If a cold front was coming, we would see more vertically developed clouds. For example, cumulus and cumulonimbus. Now the next topic that we need to talk about are low and high pressure. And low and high pressure are important because, I'm just going to make a little extra space here in this one. Low and high pressure are important because low and high pressure are how wind happens. So if we look down from the top, what we notice is that the air is constantly flowing from this high pressure zone into this low pressure zone. It's got this curve to it. And the curve to it is caused by the Coriolis effect. Now, the big key here, key idea, air always flows from high pressure to low pressure. This creates wind. So when you have a high pressure zone or a low pressure zone on the surface, that is what causes wind, is the air flowing from one to another. Now I encourage you to watch the video. But some key points include that spinning of air and water currents is often caused by Coriolis. Coriolis only affects large objects or objects traveling long distances. So some examples of that include airplanes, intercontinental ballistic missiles, hurricanes, but not toilets or toilets or bathtubs. That's because they're too small. Doesn't mean that Coriolis isn't acting on toilets and bathtubs. It just means that you're not going to see any effect on the toilet or the bathtub. The toilet and bathtub are so itty bitty compared to the scale of the Coriolis effect that you won't. The shape of the toilet bowl is so much more influential in the direction of the toilet spinning than Coriolis is. And it definitely influences hurricanes, but not the direction a tornado spins. Because once again, the spin was started by air moving at different speeds near ground level. So that's one part. The next part that we did a shorthand on is the timeline of the universe. Let's just go ahead. We're in the astronomy section, so you can see we're moving through moons. This might be a little bit out of alignment because of the space I took up. And here we are in the brief history of the universe. So we're not going to worry about the powers of 10 in this class. I'm just going to, enter the numbers for you right now, or as we go along. So this would be 10 to the 10 years ago. In the regular longer class, we talk a little bit more about that in the powers of 10 video, but this class moves so quickly that, we're not going to necessarily touch on that too much. But, getting a little comfortable with bigger numbers is important. If you'd like some videos to help you with scientific notation that's used in the book, I am more than happy. There's a really good one from Math Shorts. It's only about 4 minutes long, but it's a really good review. So, 13.7 billion years ago, this is the origin of the universe. And this is done by the Big Bang. Universe started as a single point and then rapidly expanded. 12.6 billion years ago, this is the origin of the galaxy. So, funny enough, we understand the origin of the solar system really well and the origin of the universe really well. But the origin of the galaxy is still poorly understood by scientists. And that's because gravity at big scales does not behave exactly as we would predict. This is actually the origin of the idea of dark matter. It has to do with the fact that the galaxy towards the edge isn't rotating at the correct rate. So until we understand more about dark matter, we can't understand more about the origin of the galaxy. 4.6 billion years ago, this is origin of the solar system and planets, including Earth. And this formed by solar nebular theory. In other words, solar system started as a nebula that contracted under the force of gravity. 4.5 billion years ago-ish, which should be 4.5. I know I'm being spotty with filling these exponents in, but if it says billion and there's nothing in front of it, then it's 10 to the 9. I'll just, over here, this would be 10 to the 10. If you're not understanding where these numbers for the exponents are coming from, once again, that math short is very, very useful. So 4.5 billion years ago-ish, this is the origin of the moon. And the moon probably originated by a collision between Earth and a very large, fast-moving object. 3.5 billion years ago. 3.5 times 10 to the 9. This is the origin of life on Earth. At this point, it was just single-celled. Multi-celled creatures, multicellular organisms didn't become common until about 500 million years ago. In other words, about 0.5 billion years ago. Because half of 500 million is half of a billion. So about 110,000 years ago. Now this is a real estimate. Ages date between 250,000 years ago to about 100,000 years ago, depending on what scientist you ask. So this is 1.1 times 10 to the 5 years ago. This is the origin of our species, Homo sapiens. So there were other creatures like Australopithecus and Homo erectus and Homo neanderthalis and a whole bunch of other, human-like things, but our species originated that long ago. Those other species originated much longer ago. I think it was talking in the book about 5 million years ago for hominids, but this is our species. So if you met someone about 100,000 years ago, they would look like a person. Like the person who sits next to you in class. So 1.2 times 10 to the 4, in other words, about 12,000 years ago. This is the end of the most recent glaciations. And 5,000 years ago, and I'm going to use a term that irritates some of my colleagues in the other division, but, it's useful. This is the rise of civilization. And what I mean by that is that we get writing, pottery, agriculture, etc. Which is a stunning thing to think about, because only for, we were kind of, picking bugs out of our hair for 95 to 98% of human history, and it's only been very recently that we figured out agriculture, and in a blink of an eye, we went from agriculture to spaceships. So I think that's pretty cool. So that's the video filling in on the rest of the notes. And I appreciate your patience. This, it saved 20 minutes. This lecture took 20 minutes probably in the classroom due to questions and that kind of stuff. It probably would have taken a little bit longer. But if you have any questions, don't be afraid to email me, and I'm looking forward to seeing you in class.